Welcome back to Finite Element Methods, Math 574. This is class number 15, and today is October 14th. I want to do a quick review before we get into brand new material, a review of the non-symmetric problem that we were working with last time. So we can pose that in weak form or strong form. It makes sense to pose it in the classical strong form first. So I'm looking at a problem where I'm given some f, which is a continuous function over some set omega. So that's what we usually call the forcing function. We're given some vector b in Rd and a constant c, which is greater than 0. We're looking for a u in C2 omega intersected with C1 omega bar. This is the closure of omega, of course, such that minus Laplacian of u plus b dotted with the gradient of u plus c times u equals f, if such a u exists. We're going to give it boundary conditions of a new type. So we're going to set u to be 0 on the Dirichlet part of the boundary. So that's the boundary part that's highlighted in red here. And it doesn't have to be a connected set on the boundary. In this case, we've got two boundary areas that are this Dirichlet boundary, the red boundary, and two which are this Neumann boundary. On the Neumann boundary, we're going to set the following boundary condition. Derivative of u dotted with n, or the gradient of u dotted with n, that's also called the normal derivative, is equal to g. And that's only on this blue part of the boundary, here and here. So let's assume a couple of nice things about these boundary segments. So their union should be the whole boundary, and their intersection should be empty. Now, I could allow their intersection to be a handful of points, but it doesn't really matter. The measure of these two boundary sections should be greater than 0 if I'm measuring with the d minus 1 dimensional Lebesgue measure. So this is an example where omega is an R2. And always, if you look at the boundary of an R2 domain, it's a one-dimensional, it's like a line or a curve, and its measure in 2D Lebesgue measure is equal to 0. But if I look at the measure in one space dimension lower, in one space dimension, that is, then of course it's just a line length. And we just require both of these to have a line length which is greater than 0 in 2D. And in 3D is a little more complicated. It's going to be a surface area measurement. So let's formulate a weak version of this problem. So first of all, we need a space. And the space that we need is going to be a subset of H1 such that V is equal to 0 on that part of the boundary where we're setting boundary conditions of the Dirichlet type, gamma D. So that's the space we're just going to call V for lack of a better term, or lack of a better notation. And it is, in fact, a linear space. If I take any two functions that have this property, and they're from H1 in the interior, and I add them together or subtract them or make a linear combination, that gives me another function which is again in this space. It also turns out that this can be, under some very mild assumptions, this can be understood as a Hilbert space. And it has a norm which is equivalent to the usual H1 norm. It has an inner product which is equivalent to the usual H1 inner product. Okay, then using integration by parts, we want to multiply by a test function from that space V, to multiply both sides of this equation by that test function and integrate by parts on that term. Okay, so I've set this up so that once I multiply by a test function of all four of these terms, I'm going to take these ones that don't involve the Laplacian u, and I'm going to move them over to this side with f. Of course, I multiply by a test function and integrate, and so that gives me these three terms on. Now I'm going to throw those, I'm going to think of them as being on the left-hand side, but ultimately they were on the right-hand side, equal to minus the integral, right? L2, well, just the usual integral of Laplacian u times v. And now I'm going to integrate that by parts in the usual way. In fact, you can kind of take this as the definition, and, or this is the integration by parts formula that I'm using. We throw a derivative from Laplacian u onto v, so that gives me gradient u dot gradient v, L2 inner product, and then I get boundary terms. I can write it all as one boundary integral minus the integral over the boundary of n dot grad u. This is what we call du dn. This is the outward pointing unit normal on any point on the boundary, times v integrated over the boundary. I can now break this into its two distinct regions. And now, of course, I need those regions to be measurable. And so I'm not saying what are all the details of my assumptions here. I'm simply going to say they're reasonable assumptions. So if those are measurable sets, I can break them into integral over those two measurable sets. And of course, they are the Neumann part of the boundary and the Dirichlet part of the boundary. Now, on the Dirichlet part of the boundary, my test function itself is equal to 0 because it's coming from that space where v is equal to 0 on gamma d. This is not equal to 0, this guy here, but I can notice that my boundary conditions suggest that du dn should be g. So that guy goes away, this guy transforms into that term. Okay, now I can rewrite everything in weak form. I can move this guy over to the right-hand side with all these other terms. Actually, I'll move these guys back. And so I get this weak formulation. Find u in v such that, well, I said that wrong. Find u in v such that AUV equals LV for all v in the test function space, where AU is equal to this bilinear form. It's still bilinear, but it's not symmetric anymore. This term is symmetrical. This term is symmetrical. I can interchange v and u, no problem. But this term is not symmetrical. I cannot interchange the roles of v and u anymore. Now, for my quote-unquote forcing function, the LV, that just becomes the integral of f against v plus, and that's a bulk integral or an integral over the domain omega, plus I'm going to have an integral over the Neumann part of the boundary. Okay, and so that integral is going to be given by this guy here. So integral of g against v, but it's only evaluated on the boundary, or at least that portion of the boundary where Neumann boundary conditions are enforced, so-called gamma n. All right, so actually the way I have it written here is I started with the classical solution to this problem. I integrate, multiply by a test function and integrate by parts, and I automatically get that if I satisfy the boundary value problem above, the non-symmetric boundary value problem above, then it satisfies this formulation. And now I want to give the really specific definition of what I mean by the weak solution, or the solution of the weak problem. The following is a weak formulation of the non-symmetric problem 1411. Given f in L2 over all of omega and g in L2 over the part of the boundary which is on which the Neumann boundary conditions are enforced, so-called gamma n, C greater than 0 and B a vector. We're going to look for U in V. Now, the nice thing about U in V is that it doesn't require two derivatives. It doesn't require two derivatives to be continuous even. It only requires one derivative, and that derivative can be a weak derivative. Okay, so we're looking for U in that space such that 14.2 holds. What was 14.2? That was our weak version of the equation. And if such a U exists, then it's called a weak solution to 1411. 1411 is the strong form. So a weak solution to 1411 is actually given as the solution of 14.12. Okay, so that's it for the review. So now we have in our possession an understanding of the non-symmetrical problem. We have the strong formulation of it, and now also the weak formulation of it. And now we want to decide or figure out whether or not a solution to the weak problem exists or not. It turns out it's much, much easier to determine the existence and uniqueness of solutions to the weak problem than it is the strong problem. So the space defined in 14.4 is in fact a Hilbert space. It's actually a closed, a topologically closed subspace of a Hilbert space, so it has to be a Hilbert space. The fundamental, the functional L, not fundamental, but functional L, which takes functions in V and maps them to R, is linear and bounded. The bilinear form that I defined above is in general non-symmetric, but it's unconditionally continuous. In particular, there exists a gamma, which is greater than 0, such that the absolute value of A, U, V is less than gamma times the norm of U times norm of V for all U and V in the Hilbert space V, capital V, where gamma is, it turns out to be equal to 1 plus the norm, the Euclidean norm of B. B is just a vector. It's like a known thing. It's a fixed vector. It's not dependent on space, plus that constant C, which is also positive. Furthermore, A is coercive, provided that beta, which is defined as the minimum between 1 and C, is bigger than, strictly bigger than, that Euclidean norm of B divided by 2. And in this case, well, if this is true, then the coercivity that we can write is AUU is greater than alpha times the norm of U. Of course, we're measuring the norm in H1 because we're working in the subspace of H1, where alpha is equal to beta minus the norm of B over 2, Euclidean norm. Now, how do I know this is positive, which is what I need for coercivity? It's positive because my assumption is that beta is greater than this quantity here, and that makes alpha a positive number if that's true. Under these conditions, there exists a, let's see, oops, that's not correct there. That should be, let's correct that. Should say under condition 15.1. Under condition 15.1, that's their assumptions on the parameters that were given. There exists a unique weak solution U to 14.11. In other words, there's a solution to 14.12. The proof that V is a Hilbert space, first of all, is left as an exercise. What you can show is that if I have a limit, well, you show that V is a topologically closed subspace of the Hilbert space. So how do I do that? How do I show that it's a closed subspace? Well, you show that if a sequence is convergent, then the limit point always has to remain in the subspace. And if I do that, that shows that V is topologically closed, and all topologically closed subspaces of Hilbert spaces must themselves be Hilbert spaces. So that's how that exercise would be carried out. Then the rest of the conclusions follow from the Lax-Milgren lemma, provided we can prove the other parts. That is, provided that we could show that number one, um, L is a linear functional, bounded linear functional, and that A is a coercive and continuous bilinear form. If I can show those, then the Lax-Milgren lemma kicks in for the non-symmetric case, and we can prove the existence of the unique weak solution. All right, so first of all, L is a bounded linear operator. The fact that it's linear is clear, so I don't have to write or do anything there. L is going to be a linear operator, and so I'll leave it to you to show that very small, very short detail. To show that it's bounded, we need to show that the absolute value L of V is less than some constant times the norm of V. So let's see if we can figure out how to do that. Well, by definition, L of V is what? L of V is kind of far up here, right here. That's L of V. So there's two terms in L of V that I need to analyze. And one is very, very straightforward and simple, and one is a little bit trickier. So let's use a triangle inequality that says that absolute value of L of V is less than or equal to the absolute value of that first term that I mentioned and plus the absolute value of the second term that I mentioned. Now, using the Cauchy-Schwarz inequality, I can use it on both of these terms. I get, applying Cauchy-Schwarz to the first one, this is less than the L2 norm of F times the L2 norm of V. How about this term? It's treated very similarly. I get the L2 norm of G and the L2 norm of V. But notice that both of these L2 norms are not for the whole set omega. They're only for some part of omega's boundary, in particular the Neumann part. Now I need to use a trace inequality because I need to move this. I need this to be something like an H1 norm. So what do I do in that case? Well, if the boundary is sufficiently nice, I can do this using what's called the trace theorem, or some small modification of the trace theorem that we gave from lecture 6. So if we use the trace theorem, then we can say that the L2 norm over gamma n of V is less than some constant, Ct, times the full Sobolev norm H1 over the interior of the set omega. Okay, so this is kind of this is a norm on that big set. So this is omega, but gamma d or gamma n is some portion of that. So in this case, maybe gamma n is like that, and we have gamma d is being all the rest of it. So what I'm talking about is I'm trying to control the L2 norm of V on this boundary based on the L2 norm sorry, not the L2 norm, but the H1 norm over this set omega. And the trace theorem allows me to conclude that as long as my boundary is sufficiently nice. And all that's really required is that portion of the boundary which is encompassed by gamma n should be a Lipschitz function. Okay, it should be a Lipschitz boundary. If that's true, then this trace inequality will hold. So now all I do is replace this with the trace inequality that I just developed. So L of V in absolute value is less than F plus CT, so that trace constant, times the L2 norm of G. I don't care what G is. G doesn't even have to be defined outside of gamma n. But V certainly is defined outside of gamma n. And so remember, we need a trace inequality to tell us whether or not um, its boundary values actually make sense. In this case, it does. So what did I do here? So I said that this quantity here is less than the H1 norm of V. Is that true? Yeah, because the L2 norm is contained within the H1 norm of V. And this guy is controlled by H1 through the trace inequality. So both of these terms are controlled by some constant times the H1 norm of V, both of them. And so I can take the H1 norm of V outside of the parentheses using distributive property, and I can show that this is ultimately less than this times that. Now, all this stuff in here is just data. It's given information. That's what we call data in a PDE problem. And so this can just be lumped up into one big giant constant, which I've done here. So this shows that L is a bounded linear functional. I didn't show you that it's necessary, or that specifically that it's linear, but that's easy to show. And I made some note here that to the following effect, that if we want to use the trace theorem or the trace inequality, then we need to know that the boundary, um, that part of the boundary which has the Neumann boundary conditions on it, the Neumann part, is sufficiently nice. And it should be good enough if we just assume that the whole boundary is Lipschitz continuous, and maybe one small other um, detail, but I'm not going to go into that detail here. We'll just assume it's nice enough that the trace inequality can be applied. Okay, so that takes care of the boundedness of the linear functional L. The next step is we want to show that A is a continuous bilinear form. Well, I guess I suppose before that, one had ought to show that A is actually a bilinear form. That, and so you recall my definition of bilinear form, or the only sensible definition of a bilinear form. A is clearly going to be bilinear. So you can check that part yourself. So let's go right into the continuity of A. Suppose that U and V are arbitrary, then we need to show that this quantity in absolute value is less than a constant times the norm of U times the norm of V. So let's see if that happens. First of all, apply the triangle inequality. If we apply the triangle inequality, then we now have three terms to deal with. The first term is dealt with by Cauchy-Schwarz. The second, or the last term, is also dealt with by Cauchy-Schwarz. And the only question is, how do we deal with this middle term? So I'm going to leave it as an exercise for you guys to show that this term is less than the Euclidean norm of B times the H1 seminorm of U times the L2 norm of V. Now, once again, the H1 norm has the H1 seminorm and the L2 norm built into it. Okay, it's kind of well, let me just remind you. So if I have the H1 seminorm of V, that's equal to the square root of V's L2 norm and V's H1 seminorm squared. Okay, so certainly this will control the L2 norm of V, and it will also control the H1 seminorm of V. Both of those norms are kind of already in there. Okay, so it's easy to conclude or replace this and this with their larger norms. That is the H1 norm of U and the H1 norm of V. And similarly there, and here, I just replace that with a larger object, namely the H1 norm of V. Same here, same here. And so ultimately, I can use a distributive property to pull out the H1 norm of U and the H1 norm of V. And the constants that are left over when I do that distributive property are going to be 1 from this term, norm of B from the second term, and finally C from the last term. So all the sum of those three constants are what I'm going to call gamma. And so this shows that A is a continuous bilinear form. Okay, the harder part is showing that A is coercive. I have to show a lower bound for AUU. So you replace the test function by um, the function U. And so by definition, this is equal to these three terms. Now, it's not clear why I'm going to do this, but let's start off with examining this term and putting a minus sign in front of it. And you'll see why I want to do that momentarily. And let's evaluate or let's estimate this term from above. If I do that, then by using the same trick by which I used to get the upper or the upper estimate here of that term, I can use that same trick to get a similar estimate for this term. Okay, the only difference is that it's U and U and not U and V. Okay, so, right, so I think I have another typo here. Now, what if we estimate this from above and this from above just by both of them by the H1 norms? Okay, well, what I get then is that each one is less than the H1 norm, so the product, of course, is when I do those estimates of this product, then what I get is this term is less than norm of B, Euclidean norm of B, times the norm of H1, the U, or the H1 norm of U squared, okay, because I have two terms there. This estimate, however, isn't optimal. It's a little bit lazy, and we can do better. And the reason why we might want to do better is because we can show that a wider range of parameter values actually yield a solvable problem if we do a little bit more work. So how can we fix this non-optimal estimate to be optimal or tighter estimate? Well, we can use the algebraic geometric mean inequality. The AB is less than, and sometimes this is called Cauchy inequality. AB is less than or equal to A squared over 2 plus B squared over 2. Very easy to prove this just by, well, the proof is just a couple lines. I know that A squared, let's see, how is it done? I think it's A minus B quantity squared. It's greater than 0, greater than or equal to 0, but this is equal to A squared minus AB plus B squared, right? And why am I losing? Ah, right, because that has to be a 2. Now divide by 2 and move this guy over to the other side, and you get the inequality here right away. So very easy to prove, very powerful in its use. So how am I going to use it? Well, at this stage here, I'm going to break this into the following terms, following product. I'm going to take half of B, the B norm with this term, and I'm going to take the other half with this, right? So I hope you agree that I haven't changed anything and I can use equality here. I'm going to treat this as A and this is B, and now in this inequality, so I have A times B is less than A squared over 2 plus B squared over 2. That's the algebraic geometric mean inequality in action. And then I just realized, well, what I have here is, well, these two terms are the same, right? This one and this one. And so I can pull that common factor out, which I've done. So I retain equality. And I have the L2 norm squared of u and the H1 semi-norm squared of u. If I add those two together, then that's just the H1 norm of u squared. And so now you can see that if I did a little bit more work on this term, I can show that it's not just less than this term, but it's less than something smaller, something with a tighter bound, namely less than or equal to the Euclidean norm of b over 2 times the H1 full norm of u squared. Now, the reason why I did that is because I'm going to flip the sign on this guy now. I need to get a lower bound on these three terms, by which I mean I need to find a lower bound on each one of these three terms possibly. So how do I find a lower bound on this? Well, I just found an upper bound of its negative. To get a lower bound of that term, I'm just going to multiply both sides by -1. So that gets rid of this, turns it into a plus, and it flips the sign here, and it adds a minus sign there. So in other words, the inequality that I just proved is equivalent to this inequality here. Now, take AUU, and for each term, I'm going to provide something, prove it as, or replace it with something which is smaller than it. Actually, I don't need to do anything for these two terms here and here because those are already norms. The only thing I have to worry about is replacing this with something smaller. So the something smaller that I'm going to use is, instead of using that, I'm going to use the something smaller over here. That goes there. But it comes with a minus sign. Minus signs are bad when I'm trying to prove coercivity because I'm trying to get some sort of tight lower bound. Okay, so I'm going to combine these two terms together and look at what I've got there. Well, one of these two coefficients out front of here, 1 and c, is going to be the smaller of the two. And I'm just going to call beta the smaller of those two constants. Well, if 1 is the smaller constant and I replace c by the smaller constant 1, then I get a 1 in both locations, and beta would be 1 here, and I could combine these two guys together as I've done. Okay, if c is the smaller of the two, then I'm going to replace this 1 by the smaller constant c, and I still get beta because beta is defined as the smaller of the two anyway, times, well, that smaller constant times this sum. Okay, so if I examine these two constants, these two coefficients here, and find which one is smaller, I can use the smaller to replace the other, and I can get this term as the lower bound for these two. This I'm just going to keep along for the ride. Now, what do I notice about this again? Once again, that's an H1 norm squared. And I have an H1 norm squared here. I can combine those two using distributive property, and I can remove the common factor of the H1 norm of u squared, and whatever is left is going to be actually alpha. Okay, it's just going to be this minus this term. Okay, beta minus this term is what I called alpha up above. And I said, by my assumption, alpha has to be greater than 0 strictly. So now I have AUU is greater than or equal to alpha times the H1 norm of u squared, with a constant alpha that is bigger than 0, strictly bigger than 0. So that's what we mean by coercivity. So now I have that L is a bounded linear functional, A is a continuous bilinear form, and now I know that A is a coercive bilinear form. So now I have everything I need to put together, or to use the Lax-Milgram lemma. And that says if I have all those pieces that I just described, and you go back and look at it, what it says is that you have a unique solution U to 14.12. That is my weak formulation of the non-symmetric problem. using the Lax-Milgram lemma, a unique solution to 14.12 exists, and I'm done. Okay? As long as I have continuity, coercivity, and I know that L is a bounded linear functional on V, I'm done. So that's why, so let me go back and say again, why did we do that extra little bit of work to get this constant smaller? The reason is because if we hadn't, then this alpha would have been equal to beta over, or beta minus the norm of B over 1. There'd be no 2 there. This would be a 1. And so that says that actually this B has to be smaller than with the refined estimate. And so that's restrictive. What the tighter and the more optimal estimate does is it shows that we, with a wider range of parameter values, or in this case, parameter vectors, we have a solution, a unique solution for our non-symmetric problem. So going the little extra mile allows us to show with a broader range of parameters, I actually can expect to have a unique solution. So that's why we did the extra work. So even though I think up until now, all of the problems that we discussed are symmetric problems, we now see we have a non-symmetric example where we can guarantee that we have a unique weak solution. And now the next questions are, well, maybe I want to do a finite element analysis of this, or a finite element approximation. Can this be done? And the answer to that question is yes as well. So under assumption 15.1, that is to say that beta, which is the min of 1 and C, is strictly greater than the norm of B over 2. Then the Galerkin approximation, U in VH. What is VH in this case? What should we take for our VH? Well, VH we're going to take to be the set of all functions V in MR. Remember, this is my piecewise polynomial space, polynomials of degree R. But we're going to require that the functions from MR should be 0 on some portion of the boundary, namely gamma D. So what we need here is we're going to probably need a polygonal domain, right? As usual. So I didn't say anything about that. All right, so let's suppose that, let's see. So this is gamma D. So it's this set there, okay? And gamma n then is everything that's left. Those three faces. Okay, so whenever I make my triangulation, this is actually going to require something pretty specific. I need to look for functions that are in this piecewise polynomial space, globally continuous, but whenever I look at each triangle, the function is going to be a polynomial of degree R. And it has to have this restriction that the function, when I restrict to gamma D, this part here, it has to be identically equal to 0. Well, that means I can't have my mesh being arbitrary. What I really need is to have the mesh lining up nicely with the boundary. So I can have something that looks like this, right? So these boundary edges here of these triangles have to line up perfectly. What I'm not allowed to have is something which looks like this. I would not be allowed to have one of my triangles doing something like that. Okay? So the triangle edge here couldn't, this would have a triangle which has one of its edges in gamma n and one of its edges in gamma d. That would not be allowed. Okay, that would not be allowed. I'd have to resolve this by saying, okay, well, I'm gonna fix this by making sure that my triangle resolves like that. So the requirement would be so the edges of these triangles that are on gamma d must be entirely in gamma d and can't have some of its portion be in gamma n and vice versa. Okay, if that's true, then this is always going to be possible. Okay, so I didn't go into that detail when I wrote out this notes, but just make sure that you understand that not all meshes of this polygonal domain would work. I have to have uh, full edges on gamma d and gamma n. And I can't have a triangle which has an edge, one of its edges in gamma d and another in gamma n. That just wouldn't work. All right. So this is the approximation space, the finite element space that I'm going to use. And what my result is saying that there's going to be a Galerkin approximation which satisfies this equation as it usually would, where A and L are defined as above. So this is for my non-symmetric problem. Okay, so 14.13, that's where I defined A and L. So you can go back up there to look at those if you need to uh, turn up quickly. But why am I guaranteed that this Galerkin approximation is going to exist? Well, I guess I'll give the proof as I'm making the statement of this proposition. This is also due to the Lax-Milgram lemma. And that's because if I can construct this space in the proper and appropriate way, it's going to be a Hilbert space. Every finite dimensional subspace of a Hilbert space is also going to be a Hilbert space. So this is itself a Hilbert space. I can use Lax-Milgram lemma to guarantee that this problem has a unique solution. I don't have to resort to figuring out whether the stiffness matrix is going to be of the appropriate type. The stiffness matrix in this non-symmetric case is not even going to be symmetric. So I can't examine the positive definiteness of that, the symmetric positive definiteness of that stiffness matrix. It's not even symmetric, so how could I know that it's symmetric positive definite? You have to use a different technique, and the technique I'm going to use that works is just applying the Lax-Milgram lemma directly. So we know that the Galerkin approximation exists. If that's the case, then we can know that UH exists, and we can apply Say's lemma to show that U minus UH in the H1 norm is less than a constant times the infimum of V taken over all infimum taken over VH of U minus V, H1 norm. So that's just Say's lemma. So I don't need to do anything different there. That already holds. So I already have existence and uniqueness of a solution. Where did I say that? Existence is unique. The second part is this estimate. That comes from Saya, so nothing to do. And then finally, if my mesh is a shape regular family of triangulations, and that tells me how to construct MR and ultimately VH, then I can use my interpolation error estimates to show using in combination with Say's lemma that U minus UH, that's the error, measured in H1 norm is less than a constant times H to the R, U, the HR plus 1 seminorm of U. And all I have to do is assume that to get all this is that U is in HR plus 1. Okay, so I've already told you what the proof is. Existence uniqueness comes from Lax-Milgram. Say's lemma is the next step, and then the interpolation error estimate on shape regular mesh families is the last step. That's it. Everything is done. We don't have to do anything extra. Now, in the symmetric case, we argued that, well, we could show that we could get an L2 error estimate. And so the next question that might pop into your mind is it possible to get an L2 error estimate for this problem? And so that's the next thing we want to investigate. And to do that, we're going to prove something called the Aubin-Nitsche Lemma. And remember, we used Nietzsche's trick to get the L2 error estimate for the symmetric case. The Aubin-Nitsche lemma is what takes place of that trick that we used before. We can't use this exact same trick because we used symmetry somewhere. And so now that we don't have symmetry, what can we do? So this is the answer to that question. Suppose that A is a coercive and continuous bilinear form, but not necessarily symmetric. On V, which is assumed to be a closed subspace of H1. So let VH be a finite dimensional subspace of V, and we're going to assume that VH is a subspace of MR. So this piece, basically we're assuming that we're using piecewise polynomial finite element spaces. Suppose that F is an L2 function, and that U satisfies this problem and U satisfies this problem and UH satisfies this. So this one is my weak form and this one is the Galerkin approximation. Now, how do I know that these two exist and are unique? Well, I need to assume that that A is what? Is continuous and coercive. And so since I have that, I can use Lax-Milgram lemma to guarantee these solutions of both of these problems. Then I can show that, and we're going to show that, U minus UH, the error in L2 norm, is less than a constant times the error in H1 norm times a factor. And later on, we're going to show this factor is essentially no bigger than H. But right now, all we can say about it is it's a crazy complicated factor which involves a bunch of terms. I'm not even going to try to say it. It's a supremum and an infimum, and it's much, much easier to prove this than it is to actually state it. So don't worry too much about this. We're going to later show in the best case that this is just less than H, our mesh spacing. Where this function is quite important. It's phi g. What is phi g? Phi g is the unique solution to what we call the adjoint problem. Okay, adjoint problem. And what is the adjoint problem? The adjoint problem is just kind of a reversed backwards version of the weak formulation of a problem. We're saying that phi g satisfies the adjoint problem if A v phi g is equal to GV in L2 for every V in V. So you're given a function G. If I'm given a function G, then I can ask, well, what is the solution to this weak form problem? And the only difference beyond this from the usual problem that we face is that, well, my unknown is in the wrong spot. It's put into the right-hand slot rather than the left-hand slot. Now, does this matter much? Does it matter a hill of beans? The answer is no. Lax-Milgram lemma doesn't care whether or not your unknown is in the first slot or the second slot, the left or the right. It'll still guarantee that you actually have a unique solution to this problem as long as G is nice enough. And it is here. G is usually given as an L2 function. Okay, so again, this involves something. This is we're going to show later is less than H, but it involves some weird function called phi g, and phi g is given g, it's the solution to the adjoint problem here for a given g. All right, so how do we prove this complicated estimate 15.5? Start by recalling the fundamental Galerkin orthogonality. That says that A, E, V is equal to 0 for all V in VH. So that's what we called fundamental Galerkin orthogonality. I hope you remember that. Now, when we proved it way back when, we didn't call this thing E, we said it's U minus UH. But that's just the error, okay? And so we can put E there rather than U minus UH. For any G in L2, we're now we can now observe that because phi g is the solution to the adjoint problem, then since E is at least well, E is an H1 function. Well, actually, we can say a little bit more specifically that it's in V. V is that closed subspace of our Hilbert space H1. Okay, so if this satisfies this equation for all V in V, then certainly if we choose a specific function from V, then it's satisfied, right, for that specific one. Okay, so for any G, we can put, we know that this has a solution, that's our solution to our adjoint problem. We can put E in as a test function because E is the difference of two functions from V. Now, fundamental Galerkin orthogonality guarantees that A, E phi G minus V is equal to GE. Well, why is that true? We know this, and this quantity here, that portion of it, is just 0. Okay, and I can use the linearity in the second component to bring that factor out or that term out, and you realize it's just 0. So all I'm doing is by putting in this V from VH. It has to be from VH. That V from VH. All that we're doing we're changing it by nothing. We're just adding 0. Okay. So now let's start by flipping this around. Flip through that there. Let's start with the estimate of this. Okay. So that's the L2 inner product of G against E. That's equal to, through this argument here, A, E, phi G, which is the solution to the adjoint problem above, minus V, where V is anything that I want from the finite dimensional subspace VH. Now apply what? This one is just going to be Cauchy-Schwarz. Apply Cauchy-Schwarz. Actually, no, it's not Cauchy-Schwarz. What is that one? It's simpler than Cauchy-Schwarz. It's continuity, right? It's the continuity of the bilinear form A. Okay, so apply the continuity that we know exists for A. The usual continuity constant is what we call gamma, and alpha is the coercivity constant, so we get that. Now this holds for any V that I want to use from VH. So I know that it holds for the infimum, right? So take the infimum, and so using this estimate above, taking infimum, I just get this estimate. And this is for any given G that I want to have, okay? Any given G. So that seems strange that I can use any G that I want. So, well, G appears on this side and this side, okay? So it's kind of makes a little bit of sense, but where are we going to use this? Where are we going to use this? So it's a simple exercise, and I'll make this a homework exercise so you guys can practice, that the L2 norm of U is equal to the supremum taken over all V in L2 of the absolute value of the inner product of U against V divided by the norm of V. This is equal to the L2 norm of U. So it's an exercise. Now you may or may not have seen this before. If you've taken a course on measure theory, then you've probably seen it. If you haven't, then you might not have seen it before. but it just follows from the Cauchy-Schwarz inequality, really. It's not too much harder than that. So if I want to estimate, let's say, E in this case, the error, then E is going to go here and here. And instead of using V, I can use something like G. So using that identity, the L2 norm of E is less than the supremum taken over all G and L2, the absolute value of EG L2 divided by L2 norm of G. And now we already have an estimate for this term here. And that was given by that. Now you might say, you might cry foul and say, well, I want it with E here and G here, but I have G here and E there. Well, L2 inner product is symmetric, so I can move them back if I want to. Okay. But in any case, this 15.6, I'm going to insert now right in this location. That's going to give me something which is larger. I'm still taking supremum, but now over quotients which are larger than they were before. So the new quotient on taking the supremum is going to be all this jazz here. But now if I just notice that this is a constant, constants come out of supremums. So I can bring those constants out. That looks like a typo, but it's just so that's H1 right there. Okay. Now all that's stuck in the infimum is all this stuff, but that's exactly what I said was in our estimate that we wanted to prove. And I told you don't worry too much about what's in there, because later on we're going to show that that goes away. This is what's called the Aubin-Nitsche Lemma, this guy here. And this is called the Aubin-Nitsche estimate. How do we use that? How do we use this little estimate? I'm going to give you a really quick demonstration of how this is used, and then we'll come back to what it's good for. So suppose that phi g in V satisfies our adjoint problem given some V, or sorry, given some G. Assume that the elliptic regularity holds for this problem. That is, there exists a CR greater than 0 such that for every G in L2, it follows that not only do we have a solution, but we have a solution with better regularity. H1 intersected with V or with H2. Okay, I could put V here as well if I wanted to. But it has this boosted regularity of H2. And furthermore, the H2 norm of phi g is less than that regularity constant that I said existed there, CR, times the L2 norm of G. Okay, so we're going to assume that elliptic regularity holds. If that holds, then the L2 norm of the error is less than C times H times the H1 norm of the error. And all I'm going to do is use Aubin-Nitsche Lemma that we had before. Okay, so let's get into it. To use Aubin-Nitsche Lemma, first I'm gonna point out that phi g is in H2 by our elliptic regularity assumption. We said it's better than H1 is in H2. But H2 embeds continuously into C0 omega bar. It's phi g has a representative in its equivalence classes, which is a continuous function over the closed set omega bar. And so let's look at that infimum that appears in the Aubin-Nitsche lemma. What we have inside of there is going to be phi g minus v h1 norm, and we take the infimum of v over vh. Well, I'm going to replace this infimum by using the interpolant of phi g. Why do I care about the fact that it's this function is continuous? I'm going to use the fact that because it's continuous, it has an interpolant. The interpolant that I want to use is going to be in the interpolant, which gets us into VH. Okay, whatever that was. Remember we said VH in this case In the previous case, it was going to be a subset of MR, but all I care about in this case is that it's going to be a subset of, it's going to take us into VH intersected with M1. What is M1? Piecewise linears, and that's all I need, just piecewise linears. All right, so this is going to be a piecewise linear interpolant, um, but it's got to go into the subspace. What do we mean by the subspace? We mean it has to obey the right boundary conditions. Okay, so now using elliptic regularity in that boundary condition or in that estimate, remember this is just interpolation estimates right here. If we have a nice interpolant, then the interpolation error measured in H1 can be said to be less than a constant times H times the norm of the function or the semi-norm of the function that we're trying to interpolate, which in this case is phi g. So now if we put that together, the only other thing is we want to replace this H2 semi-norm of phi g with the G norm, okay, L2 norm. And that just comes from elliptic regularity. Okay, we get an elliptic regularity constant, blah, blah, blah. Now, then all we have to do is investigate this whole business, which is that part of the Aubin-Nitsche lemma, and it has all these terms in there. Well, let's take this part here and replace it by that. Okay, so we're going to replace that by all that. Well, what happens is the L2 norm of G's cancel, and we lose all dependence on G. So G goes away. We don't have to worry about taking a supremum. All that's left over when we do that cancellation is a bunch of constants times H. And in fact, just two constants, C and CR times H. So I'm just going to resolve that as a single constant times H. All right, so what did we prove? Well, all that we said was we started with Aubin-Nitsche, which has this and that really odd looking complicated term here. And I said, well, that odd complicated term can simply be replaced by a constant times H. That's great because that allows us to maybe get an L2 error estimate even in the case of our non-symmetric problem. So can we apply this directly to get an L2 error estimate for the non-symmetric problem that we exhibited above? No, the problem is we can't do this unless G is equal to 0. Why? Well, because remember the formulation was AUV equals LV. And we can't really deal with terms which look like this. We need it to be something like AUV is equal to FV L2. And we have this extra term over there that the Aubin-Nitsche lemma doesn't know how to deal with. It's a different G here than in the Aubin-Nitsche lemma. So, but if G is equal to 0, then we can get an L2 estimate as before. We can put these two things together. And so we start off with the lemma that or the estimate that we get from Say's lemma, and we can use the corollary to the Aubin-Nitsche lemma, this corollary here, 15.4. We can combine those two things together, and we can get an L2 error estimate, even for our non-symmetric problem. Okay? We're done with this lecture. I've gotten through all the material I wanted to get through. And so we'll just finish there and I can take your questions.